Hello everyone, and welcome to today's live broadcast, Exercise Targeting Neuroplasticity in Parkinson's Disease, presented by Giselle M. Petzinger, MD, Associate Professor and Clinical Scholar in Neurology and Movement Disorders. We are excited to bring you this educational web seminar presented by LabRoots, the leading scientific social networking website and provider of virtual events and webinars advancing scientific collaboration and learning. I'm Julie Simmeroff of LabRoots, and I'll be your moderator for today's event. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. If you have trouble seeing or hearing the presentation, please click the support button at the top right of the presentation window, or use the Q&A button to let us know that you're having a problem. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, please click on the CE button located in the bottom left-hand corner of your web page and follow the process for obtaining your credits. Now, I'd like to introduce Dr. Giselle Petzinger. Dr. Petzinger is an associate professor and clinical scholar in neurology and movement disorders at the University of Southern California, Keck School of Medicine in the Department of Neurology. She completed her MD degree at University of Southern California, her neurology residency at Yale University, and her fellowship in movement disorders at Columbia University. Her research primarily focuses on elucidating the underlying molecular mechanisms by which different forms of exercise target and facilitate repair of cognitive and motor circuitry through processes collectively termed neuroplasticity. Her research involves both animal models of PD and clinical studies with patients, thus providing the foundation for a translational research program spanning the spectrum from bench to bedside. She has been funded by National Parkinson Foundation, NIH, and U.S. Army, and has published extensively in the field of PD and exercise and repair. Dr. Petzinger is also committed to promoting education of wellness and lifestyle practices to facilitate disease prevention and to improve the quality of life for individuals of all ages. Towards this goal, she has participated in developing as well as teaching educational health and wellness programs at universities both within the United States and abroad. Please join me in welcoming Dr. Giselle Petzinger. I will now turn the presentation over to her.
Thank you, and welcome to this webinar presentation on exercise targeting neuroplasticity in Parkinson's disease. What I'm going to do today, this afternoon, is present some of the work that we're doing here at University of Southern California as we try to understand the benefits of exercise in individuals with Parkinson's disease. What I'm going to do is just start off first with a traditional slide that you would see when we talk about Parkinson's disease. We think of it certainly as a neurodegenerative disorder. And this slide is pointing out that as we know Parkinson's disease, that it does represent a cell loss pattern that we see in the substantia nigra. The consequence is dopamine depletion at the level of the basal ganglia. And the clinical presentations of Parkinson's then is characterized by slowness, resting tremor, posture instability, and stiffness. But what I wanted to do was, for the purposes of this talk, is to think about Parkinson's disease in a slightly different manner. And that is a matter of circuitry itself. So the idea here is that behaviors really are the product of circuits. And so while dopamine is certainly important and is an important modulator of the circuits I'm about to talk about, it isn't behavior itself that is being manifested by cell loss of dopamine per se, but the consequence of circuit-related changes. And so what I'm showing here in this cartoon are really two circuits that we're particularly interested in when we think about Parkinson's disease. The first one is what we call the motor or somatosensory circuit. The other term for that is commonly used is called the automatic circuit. And the automatic circuit is something that is what we call practice, meaning that after a lot of practice from, let's say, walking or riding a bike, that circuit is formed, and I no longer have to think, let's say, about either walking or riding a bike. It becomes automatic, what we call non-volitional. The other type of circuit that becomes also important for motor control, and particularly movement per se, is what we call the frontal striatal circuit. And this is the other, what I'm demonstrating here is this other circuit that's coming from the prefrontal cortex, and essentially also interacting, if you will, at the basal ganglia. And so this circuit is what we call a top-down or optimizer of movement itself. It allows me to update movement as I'm moving from point A to point B. Now, the reason I'm bringing out these particular circuits, think about Parkinson's disease and dopamine depletion. As you can see, dopamine really is important. Projections of dopamine are really important in modulating these two different circuits. What we know is that in Parkinson's disease, what seems to be more impacted is really the dopamine depletion in the automatic circuit. So patients will tell you that they don't feel their movements are as automatic, and they have to think more about movement in general. So this is thought to be, if you will, tiresome and fatiguing. It's hard to constantly be thinking about movement, and so people will, they may have fatigue or may not to be able to sustain normal fluid movement because it's hard to keep processing and thinking about moving in space. So this is why in Parkinson's disease, not only do we see, again, problems with automaticity, which we know as bradykinesia or slowness, but we often see people, even upon diagnosis, it's not unusual to see what we call cognitive, particularly executive-related problems. These are problems related to working memory and mental flexibility that are common in Parkinson's disease. And one idea is that this may be happening because of this, what we call this compensatory attempt of the brain to try to make up for the loss of automaticity. The second reason why early executive problems may occur in Parkinson's may also have to do with some, again, related circuitry to changes in the basal ganglia. So basal ganglia changes can directly affect the prefrontal cortex as well. So the take-home message is that, again, Parkinson's disease, what we consider it a neurodegenerative disorder, really at the end of the day is a circuit-based problem. By the time we're seeing it, clearly problems with automaticity, often problems with executive problems that certainly, as by 5 years, a large number of patients have. And so these two sorts of problems are sort of interacting together. And so, again, the reason we think about this as we move forward in this talk is the idea of how plasticity, if you will, fits into a neurodegenerative disorder. So the way we consider that, then, is the idea that what we're talking about is plasticity at the level of circuitry itself. So let's go through some definitions of plasticity. These are rather broad definitions, but one idea, then, is just fundamentally that the brain finds a way to reorganize itself, if you will, by forming new neural connections throughout life. This is happening synaptically, so these are connections within different brain regions, and they're happening morphologically, so we're talking about changes within spines themselves, so the physical or morphological connections change, as well as functional changes in spines and synapses, and we'll go through that as we talk about some of these exercises. In fact, another idea of neuroplasticity is that the idea of homeostasis, that the brain is always trying to reach some sort of level of homeostatic change where there may be an injury to one part of the circuitry, there may be some compensatory strategies in other parts of the circuitry that may be happening at a circuit level, but probably also at a cellular level as well. And two other points to consider as we move forward in this discussion is also the very important idea that neuroplasticity really is the fundamental, what we consider a sine qua non of what we consider the encoding of new experiences and the learning of new behaviors. So ultimately, when we're talking about how to think about repair in a disorder where circuitry is aberrant, what we're hoping for, of course, is gaining new behaviors and encoding this new experience through exercise. And finally, and important for this talk, is we sort of borrow these sort of concepts that have been out there for a number of years. And what we're doing is we're introducing these concepts in the context of the damaged, injured brain. So now we're going to be talking about in Parkinson's disease, and when we talk about damage, what we're going to be really talking about specifically is circuitry, and how exercise through encoding new types of experiences may be able to drive some level of repair. So everyone knows about the decade of the brain that came out in the 90s, and of course the idea that plasticity never really ends. It may be different in the context of aging. It may be different in the context of an injured state, but it's still present. Some people also believe that in the context of injury, there may be actually what we call a window of opportunity, very similar to what we see during development, that may particularly lend itself, where the brain really lends itself to being to be able to adapt, and again, to be perhaps more quote-unquote plastic. So again, getting back to the idea of what we call neuroplasticity, we're going to use the term experience-dependent neuroplasticity, which again we borrowed from the cellular term, but in this case, what we're talking about is environmental experiences, practices that we can see certainly in children where they learn to exercise and gain better balance and gait. We certainly see that at a high level, the level of sports and athletes. And finally, what we're saying now is how we're moving through this idea towards repair. So again, in the context of Parkinson's disease, we talk about repair of particularly cognitive motor circuitry that we're interested in. All right, so everyone is very familiar with by now the exercise effects that have been reported using a multitude of different interventions in Parkinson's disease. And what you see is just an example of a number of different types of exercises that have been reported to have clear benefit at various levels, characteristics of Parkinson's, including functional measures such as gait speed and rhythm, posture stability. Also in sort of the traditional scales that we use in Parkinson's, like the Unified Parkinson's Disease Rating Scale. But more recently also, obviously, what's been reported as benefits on executive function as well. So the point is, what is the similarity, the commonality of all these different types of exercises? We get often asked, so what should I be doing, and what's common amongst what everyone's reporting? At the end of the day, what you'll find is all these different types of exercise have in common the idea of a goal-based learning, or skill-based learning. So it's providing some level of what we call cognitive challenge, where patients are having to think about what they're doing, process what they're doing, and getting better at with practice, getting better at their skill or at their goal. A perfect analogy I would use, for example, is the Olympic diver. The idea that the Olympic diver, when he first is diving, he may be having some adjustments, for example, that he needs to make on his dive. But as he gets better and better, he's getting refined in his movement and faster. And so this is a type of learning, if you will, that we are seeing in these different types of practices. What you notice too, what's very common in the types of exercise we often talk about, is particularly in gait and balance. And the rationale for that is that gait and balance really is such a high functional problem that we see in Parkinson's disease. So that's why we commonly target that in particular. So what we see now in this first video, in the first video, what I'm trying to present here is basically a patient with a Honeyar stage 3. This is sort of a baseline kind of typical Parkinson's patient who has some struggling with being able to walk. He's using his cane to walk, and also notice some struggling when he crosses even different flooring. And that's part of what we often describe as probably some problems with the updating. The cognitive process are slow, so he starts slowing down once he sees some changes in the terrain. What we see now, though, in video 2 is just an example, one of, again, many different types of examples I can show you after exercise. This is about any change in medication, and where this patient has gone through gait and balance practice to be able to show that he can move more fluidly, he can get across the mat much faster, and again, most importantly, what we're looking for is bigger amplitude, bigger stride length, bigger, larger arm swing, and so he's having a more natural, fluid gait. So I think the other thing that's important to keep in mind here is when we go through exercises with Parkinson's patients, we're not like dragging people across, on a treadmill. The idea is we apply a bigger challenge once a patient is able to, what you would consider, be successful at a type of movement. So as soon as a patient is showing that she or he is getting better at some type of amplitude movement or gait movement, what we'll do is make it harder. And so the idea, again, behind exercise is making it skillful and making it challenging by making it harder so that they're problem solving and getting better. So challenge, practice, repetition, feedback are all the types of things that we consider important for learning and certainly important in Parkinson's disease. So back in 2014, as we were thinking about some biological questions that we wanted to ask, we started thinking about coming up with some very specific hypotheses of what might be going on along the line of plasticity. What we thought about was, again, what role goal-directed motor learning may play in exercise, with the idea being that that particular idea would lend itself, if you will, to synaptogenesis. So it's back to learning. If that's the case, if people are indeed learning, then what we'd anticipate is we would anticipate seeing changes, for example, in synaptogenesis, some changes in neurotransmission. And so that was one of the hypotheses that we started putting forth. And alternatively, what we'd also anticipate is that there would be gains that may be coming from the periphery, and this may be, again, perhaps more on the aerobic exercise part of any exercise paradigm, that aerobic or increased blood flow may lead to some peripheral effects. The idea is that these are synergistic effects. One does not necessarily exist without the other, but that these two are interacting, if you will, at the level of the brain to create a permissive environment, and two, support it for particularly practice and synaptogenesis. So with that in mind, that was the hypothesis that we've been working on, and we decided to go on and begin to look at that using animal models. We had been looking at using the MPTP animal model for some time, using rodents. The MPTP is a protoxin that basically crosses the blood-brain barrier and becomes a PP+. It gets taken up by the dopamine transporter. It's pretty effective and leads to apoptosis. So in the animal model, it's a pretty nice way for us to replicate particularly changes in dopamine circuitry that we're particularly interested in. So it's not Parkinson's disease, but it is a model of dopamine depletion that allows us to begin to explore changes in circuitry relevant for Parkinson's disease. With that said, then, we decided to particularly take our exercise paradigm and look at the effects of exercise, not so much in the neuroprotective realm, but rather in the reparative realm. So with that in mind, we decided to look at exercise not before the lesioning, but after the lesioning was complete. And so most of our exercise paradigms actually begin essentially 5 days after MPTP. So we're looking, if you will, at a restorative or reparative effect of exercise, not a neuroprotective paradigm. Also, our paradigm involves essentially the use of a treadmill, and we use basically 28 days. We were also incorporating in the analysis a saline control. So we have our saline control, and we have an MPTP exercise group as well. And what you'll see in video 3 is the example of the treadmill that we've been using in the MPTP mice. And we would argue that there is definitely some cognitive challenge for these mice because it's not obviously a natural environment for them, but also because they're being forced to stay up at the front of the treadmill. So I'll show you another example of another type of exercise that our group has used, but we're going to start with this particular model, the restorative effects of exercise using a treadmill, 28 days. So let's go on to show you what we first reported back, actually now back in 2004. Some of the initial work that we had done was, again, looking at particularly the motor effects. So in this video, what you're seeing is basically 2 animals. One, they're both Parkinsonian, they're both MPTP, they both have 40% cell loss, 60% dopamine loss. The difference is only exercise. So one group obviously going through the 28 days of exercise, the other group, what we call the couch potato mouse. And we can clearly see is improvement in motor behavior. And of course, now it seems fairly obvious. If you run, you're going to get good at running. And so we certainly saw that. We also saw improvement in rotor eye performance with this group. And our colleagues in our group, Dr. Holzschneider, has also reported on other types of motor benefits, including the motor beam or the beam crossing. So we've seen other types of benefits that translate after the treadmill effect. So apart from that, then, once we started looking at the motor behavior, one of the questions, of course, that came up immediately is what effects does exercise pose on dopamine neurotransmission? So again, remember, dopamine is an important modulator of plasticity. We know it's needed for motor acquisition. That's been shown now by a number of different investigators. Dopamine is required to lead to synaptogenesis at the level of the automatic circuitry. So it's needed to acquire motor function. It's also needed for maintenance. If you block dopamine, you're going to lose motor function. So obviously, it's an important thing to look at in terms of what exercise may be doing. So we decided to look at dopamine levels. We've looked at dopamine receptors. And we looked at dopamine transporter, which is important for clearing dopamine from the extracellular space. And I'm going to show you right now what we were able to see. So this is a paper back in 2007, Journal Neuroscience. What you see here on your left and looking at the screen is basically an HPLC, where what we do is take out the whole striatum. And what you're seeing is after 28 days of exercise or 28 days of sedentary, no exercise, essentially the HPLC data showed no difference in total amount of dopamine. So again, clearly improvement in motor behavior, but total levels, at least by measure through HPLC, is not explaining this difference. What we then decided to do is do something called voltometry to look at fast scan voltometry, to look at dopamine release properties at the level of the striatum. And what you see in the cartoon there is essentially a section of the striatum, and across there are numbers where the dopamine fast scan cyclic voltometry was used to measure dopamine release. This work was done by Dr. John Walsh's group, lab, who's a big collaborator with us, and Dr. Garnick Akopian. So in this study, what they are able to demonstrate, if you look at the very bottom figure, is you see comparing MPTP, these are both MPTP groups. The difference is that in one group, they've been exercising up to 28 days, and the other group has been sedentary. What's interesting is across the board, throughout the striatum, particularly in the dorsolateral striatum, we see that there is a larger amount of dopamine being released. So what I'm trying to show is that while there isn't a total level of dopamine that's changing, there's clearly changes in the amount of dopamine release. The other thing that was quite interesting about this result was we were also able to demonstrate using immunocytochemistry with changes in the dopamine transporter. So if you look down again at the immunocytochemistry work by Beth Fisher in the lab, basically what we saw was changes in the amount of dopamine transmission, dopamine transporter protein levels using immunocytochemistry. Again, to your left is the MPTP animal, to your right is the exercise animal, so it was down-regulating. The reason this is of interest is when we went back and looked at the fast scan results of the fast scan cyclic voltometry, what we saw was that the clearance of dopamine at the level of extracellular space was also diminished. So again, we see no change in dopamine levels, but we see more dopamine being released, and we see that the clearance is slower, which matches the dopamine transporter. What's interesting about that is that we do use the dopamine transporter not infrequently in clinical trials to get some handle on, as a surrogate rather, of dopamine integrity. And all I want to show you is that when we counted cells in the 9-gram, we saw no difference in cell number. So changes in dopamine transporter are occurring irrespective of changes in cell number. All right. So finally, the other thing we became interested in was looking at the dopamine receptors themselves. What we saw, this is using something called in situ hybridization. This is looking at the level of the striatum. So this is analysis, again, of transcripts. And what was interesting about this is just that we saw, again, changes at the level of, in the striatum, particularly with D2 receptors. This was replicated by Marta Vukovic in the lab, where we saw it also at the level of Western immunoblotting. So we became particularly interested in the effects of D2. We decided to create a ligand for the D2, and with PET imaging, Angelo Naka, a postdoc in the lab, also was able to do some work with our animals. And what you're seeing here is the result of a PET image in a sailing animal, an MPTP, and an MPT exercise. Take-home message is that we saw an increase in D2 expression with exercise. So altogether, what I would say is clearly our data is showing that there is some improvement across the board of dopamine neurotransmission. So we were able to replicate this study, a paper that came out, a neuro report that basically showed that we were able to see after 8 weeks of treadmill exercise, we saw the same effect in de novo Parkinson. So let me just walk you through that. So these were patients, it's very small n here, I'm just showing you essentially an n of 4 Parkinson's de novo patients. And what we see is essentially improvement or increase in the D2 expression using a PET image with F18 phthalate, and it's a PET image superimposed in an MRI just to show you that we're seeing this effect, particularly at the level of the striatum, and none of this effect was seen in the no exercise group. All right, so now I'm going to walk you through just briefly through some cartoons, some work that was done. I want to show the bottom here. Some work that was done by a number of people in the lab showing changes in glutamate neurotransmission, and essentially we saw changes both in the AMPA receptor expression of GLUA1, where we saw essentially with MBTV an increase in GLUA1 expression. With exercise, we saw diminishment of GLUA1 expression. Charlie Mitchell, a collaborator in Oregon, was able to help using EM to show us that we also saw changes in glutamate levels presynaptically. So there's increase in glutamate storage before exercise, which was attenuated after exercise. So again, 2 points right now, AMPA and glutamate storage elevated, if you will, with MPTP or dopamine depletion, and it was normalized with exercise. Now, this is of interest because definitely in Parkinson's disease, one of the ideas is at the level of the striatum, there's a hyperexcitability, if you will, in synapses that is occurring because of dopamine depletion. So this certainly fits in with the general theory behind what we think is happening, certainly with MPTP, and that exercise, if it attenuates that, could explain the improvement in behavior. The final slide that I'm showing here is that exercise also seems to attenuate this increased activity or amplitude that we see using spontaneous EPSPs. So again, this is work done by Garnick Akopian, John Van Leeuwen, and also Natalie Kintz. So some other work that we decided to do was looking again at the dorsolateral striatum. We wanted to see if we could see changes in actual morphology, if you will. So I'm showing you changes in glutamatergic neurotransmission, changes in dopamine neurotransmission. Will Toy in the lab started to examine changes in synaptogenesis, and what I'm showing you here is a Golgi stain, again focused at the dorsolateral striatum in particular. This is the area important for the automatic circuitry, and then what we see in figure B is essentially a blow up of the Golgi filled median spiny neuron, and then on section C, what we see is effects of saline and MPTP, and then an increase that you can see with exercise with increased spine density. So the next question I want to ask is about blood flow, about whether different types of exercise matters. That was another question that we were trying to address in the lab. And so the common things that we think about in terms of types of exercise, number one is the aerobic exercise. This is the type of exercise where you're trying to condition to enhance circulatory and respiratory efficiency. This is the type of exercise you most commonly hear about, particularly in aging studies, where the idea is that you're either riding a bike or you're doing anything to get your heart rate up, essentially, versus skill-based exercise, which I would say is really the predominant form of exercise that you see in Parkinson's disease, which is, again, more goal-oriented, really focused on challenging gait and balance and getting better at movement and processing of information. And so Dr. Holschneider and Dr. Wang, our collaborators with us here at USC, essentially looked at this ingeniously by putting together a type of exercise intervention whereby animals, particularly the so we're using now a slightly different Parkinson's model called the 6-hydroxydopamine lesion rodent. This is a rat model now. In this case, we're taking animals, putting them through 6 weeks of exercise. They're either going through a skilled or complex wheel practice, or they're going through a non-skilled, what we call simple wheel with spokes all contained, so it's smooth. Now, what's interesting about the way they decided to approach this question was that both of these wheels are placed on motorized rods, so they're matched for the aerobic training. The only difference between them really is a level of skill. The question we're going to ask, they decided to ask, was whether there's difference in blood flow. And the way they approached this was by using this compound called C14 iodopantipyrine. This is a very valuable way to look at, if you will, mapping of blood flow in the brain of a awake and unrestrained animal. The way they do this is they introduce basically the catheter, if you will, essentially before the animal start exercising, and then after the animal completes their 6 weeks of exercise, it is attached to a pump, and the tag is the C14 iodopantipyrine. They're sacrificed within 24 hours, the brain is removed, and essentially they could do a type of very similar to a functional connectivity study, but in this case looking at blood flow. And what you see now in this figure, comparing against skilled to non-skilled, is basically sections of the brain where you see radioactivity, where, again, marking blood flow. The interest in this particular type of approach is what they're looking at is what's called a seeding study, meaning that if you ask the question, if the PFC, if you see a prefrontal cortex is activated, which it is in the skilled exercise and in the non-skilled, what other areas are lighting up? And what we can see, certainly with the skilled exercise, is many more, if you will, connected areas, particularly of relevance to us is obviously the motor areas, the somatosensory area, and the CPU. To a much greater degree, CPU for striatum, to a much greater degree than non-skilled. So why do we care? the reason we care is that this is beginning to give an idea, the very important idea, that the brain itself is not a passive recipient of exercise. So this is very different, if you will, than what we think about when we think about, for example, maybe cardiovascular benefits. So it's not just about what these peripheral effects are that are going to the brain and creating some sort of generalized effect. What we're seeing is that there appears to be some level of circuit specificity that's occurring by virtue of what I'm doing. In this case, by virtue of creating a greater cognitive load, I'm actually having some impact, if you will, on circuitry itself. So one of the questions we began to ask then is, could these effects be related? So the idea that you're getting changes in blood flow, could they be driven, if you will, by some underlying metabolic plasticity synaptic change? So again, getting back to the idea that these two effects are synergistic. The effects of exercise, particularly that are goal-directed, are creating learning, but there are clearly some peripheral effects that are playing a role here. And so certainly from the peripheral effects, I mean, certainly neurotrophic factors could be play a big role. Obviously, the importance of insulin, immune system, of course, are very important. How is this synergistic effect working? One idea we had, going back to some, again, other mechanisms that may underlie this brain health, we're focusing now on angiogenesis and particularly the role of metabolic capacity. I'm going to review this really quickly with you. People have certainly showed, not just in Parkinson's, but even in normal animals, evidence of neurogenesis, synaptogenesis. We see changes in synaptic strength. Obviously, changes in angiogenesis has been shown already by Black and Greenow, more recently by Wang in our group. But what we're moving on now is whether or not there could be, in terms of synergistic effect on the role of the brain, whether there may be something happening at the level of metabolic changes that may be driving, if you will, not just synaptogenesis, but also some of these effects on blood flow. So one factor that we got interested in that we thought could be of interest that might be, if you will, be activated at a cellular level. So what's happening at the level of the brain that may be creating changes, if you will, in the environment, is this factor, transcription factor called hypoxia inducible factor. So this particular factor is of interest. It's been studied by many different groups. But one of the ideas that we have essentially borrowed from these other groups is the idea that exercise, if you will, like hypoxia, exercise may provide a stressor within these cells that may drive the expression of HIF, creating some level, rather, of stabilization of HIF and leading to some transcriptional activation. Now, this is of interest because this particular transcription factor is upstream among a number of different mechanisms or pathways of interest that can support synaptogenesis and metabolic homeostasis. That includes aspects of glucose uptake, lactate metabolism, angiogenesis, and trophic factors, as well as blood flow itself. So HIF became of particular interest to us, and we began to look at that. This is, again, just reviewing what potential roles of HIF that's been demonstrated by other groups. There's also been some evidence by the Kinney group in 2011 that HIF is increased with exercise. This was repeated now by a graduate student in the lab, Matt Halliday, who's beginning to look at this, essentially looking at the level of striatum. And what we're beginning to begin to tease apart is a timeline in which we began to see changes in HIF. This figure is just beginning to show the idea of how fast HIF is really expressed. So we're seeing this expressed within 5 days of exercise. HIF is clearly getting upregulated. We see some correlation with carbonic anhydrase as a sort of surrogate marker, if you will, of hypoxia. And what's of interest is also the work, again, I'm just showing you some preliminary data. This is an ongoing project going on in the lab right now, basically showing that these other transcription factors that are regulated by HIF are also upregulating as well. This includes, again, the glucose transporter, lactate dehydrogenase, and even VEGF. So what I'm trying to put together then is this idea, as we're thinking about how is the brain involved in this benefit of exercise, particularly at the level of circuits, is that this is a synergistic effect. Exercise is really a spectrum of probably aspects of not just learning, some have more than others, but also some aspects that are beneficial, that are aerobic in nature. So when we think about exercise and fitness, what we're really thinking about is, again, a learning aspect of it that drives circuitry and learning, if you will, encoding through practice, repetition, problem solving. but also how it's recruiting and actually maybe modulating some of these peripheral effects as well. So it's a synergistic effect that the brain plays. So in conclusion, I just want to emphasize, again, some of the points we made. First of all, exercise, we know behaviorally, we know improvements in motor, more recently improvements in cognition. There's still a number of studies going on, but clearly there's compelling data that exercise also appears to be helping cognitive circuitry, particularly prefrontal, executive. We're showing you in an animal model, clearly exercise seems to be facilitating dopamine neurotransmission. And importantly, in doing so, probably attenuates some of this, what we consider a hyperglutamatergic drive that we typically see in Parkinson's disease, that seems to be attenuated by exercise. I demonstrated that through changes in spontaneous EPSCs, excited postsynaptic potentials, changes in glutamatergic storage, and also in expression of AMPA receptors. We do see, as we hope to see, that there's differences in the type of exercise you do, meaning that skill-based or by cognitively loading what you're doing with exercise, it's going to change what you're doing to activate circuitry, and we believe that change, driving some aspect of metabolism, metabolic stress, drives blood flow changes. And so this specific metabolic demand may be what underlies some of the surface-specific effects of exercise. Obviously, trying to understand how this is happening itself could lead to some very interesting mechanisms that may allow us, with exercise, to modulate some of these benefits and drive synaptogenesis and repair. So I just want to thank you for your time this afternoon. I have a wonderful group of people that I'm lucky to work with. It's certainly a team of people that I get to work with, particularly Michael Jakowick, who's a co-PI on all the studies that I've talked about, Beth Fisher, who started some of the original work with us, Marta Vukovic and Natalie Kintz, who talked about the AMPA receptors, Matt Halliday on some of the newer ideas of metabolic changes, Will Toy, particularly on the spine changes, John Van Leeuwen, who did a lot of the original work on the AMPA receptors, and now I have a large group of people that are helping us translate a lot of this now into the human work, so we have a number of different human studies going on that's trying to show evidence for changes in functional connectivity using these different types of exercise, aerobic, skill, and social. And at some time, I hope to be able to come back and talk about that work as well. So thank you so very much for your time. And that's me learning how to surf, and my other partner in crime, John Walsh, who's an expert surfer. So thank you so much. How do I get out of this? Lauren. I mean, I can't escape, but I lost my slide. Hello? You off? Did I lose that?
Thank you, Dr. Petzinger, for that very informative presentation. It's now time for Q&A. If you have a question you'd like to ask Dr. Petzinger, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. We'll answer as many questions as we have time for. If you are unable to get your question to Dr. Petzinger, we will follow up with you via email after the presentation. Let's get started. Our first question is, Dr. Petzinger, could you give examples of skilled exercise, and how do you think this compares to cognitive training?
Yeah, I'm happy to do so. So examples of skilled exercise would be anything where examples of field exercise would be any type of exercise where you're having to learn to do something better. You have a goal of trying to get better at a type of skill. So another good analogy is tennis playing. So learning to serve better, or learning to do a backstroke better. So you're challenging yourself to get better at a particular motor skill. So those are examples. But so it's not any particular exercise. There's many different types of exercise where you're getting better at it and challenging yourself. You're going to gain a skill. So that again can be Tai Chi or yoga, surfing. I've given you an example. Even biking has some level of skill, obviously, because you're learning to get better at balance, particularly moving faster. So that obviously could be considered a skill. If we looked at the literature, there has been some studies that have tried to compare exercise versus cognitive training alone. And some of that work has been done, for example, by Art Kramer. The idea is that probably skilled exercise has a bigger effect, if you will, on cognition than simply cognitive training. So the idea of a pencil to paper type of crossword puzzle, I think one of the ideas there is it doesn't have as much generalizability. And the idea is that when you do crossword puzzles, you get good at crossword puzzles. But it doesn't generalize as much as what you get from practice of a motor skill, a physical skill, moving from point A to point B. One of the ideas there is that simply because you use so much different types of sensory input, if you will, visual, spatial, sensory feedback, problem solving, that incorporates so many more circuitry, if you will, when you're practicing a skill, that you're going to gain a bigger generalizable effect. That's just an idea, but that may be what's accounting for differences. So the take-home message is that exercise, particularly skilled exercise, will have a bigger effect than just cognitive training per se. Next question.
Great, thank you so much for that answer. The next question is, do you see evidence of synaptogenesis in other brain regions besides the basal ganglia? For example, in the prefrontal cortex?
So that's an excellent question. We actually are looking, we have some data we haven't published on yet, but yes, so we see evidence in the prefrontal cortex as well. So again, that's of interest to us because we're particularly interested in the prefrontal striatal circuitry. Everything that we've reported on and published on so far has been in the dorsolateral stratum, but some of the work that we're doing right now seems to suggest that there's some involvement in the prefrontal cortex, so the answer is yes. We're also looking at some areas of the brain that we wouldn't anticipate to be much of a change with the skilled exercise. So we're trying to look at a sort of a positive control and a negative control. But some of the preliminary data we have is that we're developing is yes, there seems to be some involvement in other areas as well. Your next question?
Great, thank you. So the next question is, are the changes you observe with HIF expression circuit-specific or global? HIF expression circuit-specific or global?
So the HIF effects have been, right now, we've only looked at the level of the basal ganglia, but we would anticipate that it would be circuit-specific. There are people that have looked at HIF and show that HIF effects seem to be happening at a circuit-specific level, so it's not something that you typically see global. So we anticipate that we would see a circuit-specific effect. Everything we're looking at right now, as I said, has been at the level of the basal ganglia, so yes. To be determined, but yes, we suspect that will be the case.
Great, thank you very much for that answer. So the next question is, how long do the beneficial effects of exercise persist even after you stop exercising?
that's another great question. So we haven't, I have to tell you, we have not looked at the long-term effects of exercise. That's a project that we're doing right now. What I can say is that there have been groups that have looked at that question to some degree. It's not a lot out there so far, but I know that, for example, Carl Kottman in Irvine has looked at it in the context of neurotrophic factors. So he's looked at some of the long-term effects of exercise after exercise is terminated to show that neurotrophic factor does go down over time. But what's interesting about some of the work he's published is showed that there seems to be some sort of molecular memory to some of these, to this effect, like neurotrophic factors, so that when the animal, even though neurotrophic factor goes down over time, when the animal goes back to exercise, let's say a month later or a few weeks later, the neurotrophic factor goes up much faster. And so there is this, at least preliminary data from animals suggest that in fact there does seem to be some form of what we call molecular memory, whereby these sort of biological effects have some level of priming that may be upregulated a little faster over time. But apart from that, we ourselves have not looked at long-term effects yet. This is another very important question that needs to be addressed. Thank you. Another question?
Okay, thank you. Looks like we have time for just one more question, and that question is, what role do you think aerobic exercise plays in neuroplasticity?
Thank you for that question. So I think that's also important because certainly in the aging field, particularly in the human studies, there's been a lot that is really focused on the role of cardiovascular fitness and aerobic exercise. And there's some very compelling data that there is a relationship between that and, for example, changes in functional connectivity, changes in volumetric brain regions that seem to be getting larger. So we do think, obviously, that there is some role for aerobic fitness. And again, the idea that some of that may be because of some of these peripheral effects that the blood flow may play, either, again, at the low immune system or the trophic factors. So I'm certainly not saying that aerobic exercise doesn't play a role. I think the thing that we're trying to understand is that there probably are other elements to exercise, particularly, as we said, getting back to the idea of learning and what role that plays, particularly in driving some of these circuit-specific effects. So again, as I pointed out on that experiment that Dr. Holstein or Dr. Wang have pointed out, those animals were matched for aerobic, but clearly there was differences in blood flow simply based on skill. So I think the effects of aerobic, again, is working synergistically, if you will, with some of these what we consider kind of skill or learning-based effects of exercise. So yeah, I think it does play a role. I think what will be interesting to determine is how much aerobic, what the relative contribution is of aerobic. In other words, is it good enough to do short bursts of aerobic? And that's essentially getting the system primed, and then you're good to go to get in some learning and practice. So the contribution of aerobic may be a smaller component of what a person needs to be doing, particularly when we're talking about repair of circuitry. And the idea is maybe that skill may be the bigger contributor, and that's something we're trying to address right now in some of the human work. Thank you very much for the question.
I would like to once again thank Dr. Petzinger for her presentation. Do you have any final comments?
Final comments. I think we've been talking obviously about Parkinson's disease. I think the thing to keep in mind is the original part of the talk, and that is the idea that plasticity is relevant for all of us, particularly the effects of the environment. That, you know, this is not, it doesn't end just because you're getting, you know, you have a disorder or that you're aging. The idea is that we're the product of our environment, and what we perspective, thinking about what we do to enhance cognitive skills and getting out there in the environment and novel environments are all healthy for our brains, particularly when we talk about brain health and cognitive changes. So get out there and exercise. Thank you.
Great. Thank you once again, Dr. Petzinger. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through 3 months from live date. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again. Bye.